Hello class. So this is for this homework that we had with this handout 6-1, 6-2, 6-3. So on this question 1 here we have a disk that's rotating and we're asked to rank these in order here to where we're looking for the speed on these objects. Or rather, in this first part, we're looking for the period. So in this period here, that's the time it takes to go around in one complete rotation. And so they're all going to have the same time because this disk is going to rotate, and since it's not going to break or be deformed in any way, that if A goes around in 2 seconds, then B is also going to go around in 2 seconds. And if A is going to go around in 2 seconds, then C has to go all the way around in 2 seconds as well. And so they're all going to have the same period. And this is talking about this time, and we're going to use this letter T in order to get to that. So then in the second part, then it's asking about the speed. So we know that velocity is a change in position over the change in time, or the displacement over time. And we know it goes in one complete circle in that time t. So if they all have the same time t, then it's really the only difference is going to be the radial distance r. Because if we go in one complete circle, that's the circumference here, is 2 pi r, where we know the radius of c is greater than a and b, which are equal to one another. So since that's the case, then we're going to see that c is greater than a and b, which are equal to one another. And as I get to this backside, we were asked to get to this centripetal acceleration and these velocity vectors for t on 8. So we needed to get 8 different locations, and we were given the first location and the velocity vector. And we were asked to indicate both the velocity and the acceleration vectors here. So as I note here, the centripetal acceleration is the acceleration that goes towards the center of the circle, centripetal. So when you have something going towards the center, that's the centri. And if you were to pedal your bike, it goes in a circle. So this acceleration goes towards the center of the circle. And I also want to make the note here that the velocity vector and this acceleration vector, they're perpendicular to one another. They make this 90-degree angle. So when we go at 8 different locations, I went 1, 2, 3, 4. So I went at 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. And then I went halfway in between each one of those to make it evenly spaced, so that way I could have 8 different locations. All of them having the centripetal acceleration pointed towards the center, while the velocity is perpendicular to the acceleration and tangential to the path. So in this third one, we are having these 3 objects moving, A, B, and C, and we're to rank these based on this centripetal force, the net centripetal force. So I know acceleration is the net force divided by the mass. So to get this net centripetal force, this net force is mass times acceleration, where I know the centripetal acceleration is at v squared on r. So with they having the same mass, really what we're ranking this centripetal force by the centripetal acceleration, because the v squared and the r's are all changing. So then I just went through, I looked, well, I have a 2r here and it's moving at a v, so this is v squared on r, 2r. Then for this one, this is going at a 2v, so it's a 2v squared, and it's at twice the radius, so it's 2r. So 4v squared on 2r comes to a 2v squared on r, where this option C is just going at a v squared on r. So if I see I have a v squared r, v squared r, v squared r, where in option A it's 1/2, or v squared on 2r, so it's 1/2 of that v squared r. And then option B is 2 times v squared on r, and option C is only 1 of the v squared on r. So 2 is greater than 1, which is greater than the 1/2. That's how I'm able to get to this net force on B is greater than C, which is greater than A. So as I take us then to this 6.2. In this 6.2, we're given 2 different planets. And planet A has this density of rho naught, and it has this radial distance of 2 r naught. So I like to just underline things. That way I'm picking out this information as I'm going along. So planet A has a density and a radius of 2r. And planet B has this density that's half and half the radius of the previous one. And what we're asking here is this gravitational field. We're asking about which G is greater. And then we have to justify our claim with reasoning to support it with evidence. So with a bigger radius and denser, that means there's a lot more mass. So I tried to draw in some lines here to indicate that there's a lot more mass in the bigger object here. And then planet B, it's a smaller, so this radius is r0. Smaller radius, it's less dense, it has less mass. So bigger thing with a lot more stuff to it, smaller thing with a lot less stuff to it. I can already tell you that planet A has a greater gravitational field just by looking at with something is bigger and it has a lot more stuff to it as compared to something that's smaller, it has a lot less stuff to it. But now to get to this equationally, so we can prove it with an equation. Where I know the force of gravity acting on a mass is this mg. And the force of gravity also acting on the same mass is from the planet divided by the radius of the planet squared. So I'm going to set these two equations equal to one another. Gravity is equal to gravity. So this mg, mass of something, times g is equal to this capital G, mass of the planet divided by the radius of the planet squared. So what we can tell is that the gravitational field doesn't depend on the mass of an object. So like you or I, we don't affect the gravitational field of Earth, just like another mass on another planet won't affect the gravitational field on that planet. So I'm calling this right here equation 1. And then using density, which is mass over volume, I'm able to find the mass of a planet using the density and the volume. The volume being 4/3 pi r cubed. And I'm going to call this equation 2. So to get to this g, I use equation 1, which is that cap g, mass of planet A divided by 2r0 squared. That's the radius of A. So then I use equation 2 to find this mass of A, which is ρ0 4/3 pi r cubed divided by this r squared. So one of these terms gets dropped, so the cubed drops that squared term here, leaving us with a 2 times this 4, which is 8/3 pi ρ0 g r0. Getting the same thing for B, this g, mass of B, I use that equation 2 to get what the mass of B is divided by the radius here. And I have same thing, this cube term cancels out with that squared term, and then I just have the ρ0, which is half the density, so that 4 divided by 2 is 2/3 pi ρ0 g r0. So we see here we have 8/3 and 2/3 multiplied by the same thing in both of these. So I can then say 8/3 is greater than 2/3, so the g of A is greater than the g of B, just as we could tell in this justification. So as I flip over to this backside, so once again I have these two satellites. They're in a stable circular orbit around a distant planet. So I draw the planet, this r of A going from the center of the planet out to satellite A, going from the center of the planet out to the satellite B, where mass of the satellite is ma, and the mass of satellite B is half. So I'm just trying to indicate what I have here in the reading. And this radius here is r of A, and the radius for satellite B is double that. So I'm able to make a little table here so that way I can pull out the information that is from this problem. And in this, what we're trying to find is who has the greatest speed. Well, I know the net force divided by the mass is equal to acceleration. And the acceleration that we're dealing with here is the centripetal acceleration. And it's from the gravity acting on these satellites. So I know the centripetal acceleration is v squared on r, that r. And then this force of gravity is that mass of the planet multiplied by the mass of the satellite divided by r squared. So the mass of the satellite cancels out. These r terms cancel out here, giving us this v squared is this cap g mass of the planet divided by r. So once again, this velocity does not depend on the mass of the satellite. It only depends on how far away you are from the planet. And if I square root, I get this velocity being 1 over this square root of r, because g and the mass of the planet, they don't really change. So what we can say is this velocity is proportional to this 1 over the square root of r. So A has a radius of A, B has a double the radius, so 1 divided by square root of 2 is less than 1 divided by 1. So V of A is greater than this V of B. And then in the second one, we're asked about this acceleration. We're trying to rank these accelerations. So I do the same thing, net force divided by the mass. I'm able to get this acceleration is this does not depend on the mass of the satellite. It's proportional to this 1 over r squared. So for A, it's 1 over RA squared. For B, it's 1 over 2 RA squared. So this would be 1/4 of RA squared. So we can see that this is 1/4 of the acceleration of A. Therefore, A is greater than B. Lastly, with the two satellites, we're asking about this orbital period. From above, we had that V squared term, is that G, mass of the planet, divided by R. We know that this V is the circumference divided by the time, 2 pi r divided by t. We square that term, so I squared everything in here, move the t squared to one side, move the other r over here, giving us a 4 pi r squared, r cubed, equal to this G, mass of the planet, times this time squared. What we're seeing here is some terms over here, some terms over here. We can see that this r cubed is proportional to t squared. This is also one of Kepler's planetary laws of planetary motion. So this period squared is equal to this r cubed, proportional. So the radius of B is greater than that radius of A, therefore the period of B is greater than this period of A.